Good day, my learners. As we prepare again, I want us to go through another exercise as to how do we deal with the Euclidean geometry questions. I want to put emphasis on this because you must be aware that it takes about 50 marks on your paper 2 question paper. So I want you to really give it attention. Give it time to revise and to go through all what you have mentioned already, grade 8 and 9 work. It's very important because you see, you cannot answer some of these questions if you don't really deal with that revision. Having said that, equally of importance is all the theorems that we have learned. I'll just quickly go through with you on the theorems about the circle, the theorems that we have learned in grade 11 about the circle. Let us quickly go through those theorems. The theorems that we learned in grade 11, among them is this one that we need to be familiar and be able to recognize the diagram when we look at it without really doing the proof of the theorem, but we just quickly need to be able to recognize the diagram. This theorem, remember, it said the line drawn from the center of the circle perpendicular to the chord bisect the chord. It means it cuts the chord into 2 equal halves. Or the converse may say the line drawn from the center of the circle to the midpoint of the chord is perpendicular, because we did mention that this sign means what? 90 degrees is perpendicular. So it means it is 90 degrees. Now the other theorem that we have learned, please be able to recognize this theorem. It's very important. I just made rough sketches here quickly. The other theorem is the one about the diameter. How do we recognize a diameter? Once you see the center, it's important that you recognize the center, and the center will be given there or indicated, or it will be written down that that is the center. Then you know that once we have a line that passing through the center of the circle, that line is actually the angle there will be twice the angle that you find on the circumference of the circle, meaning that the diameter subtends a right angle here. If this is a diameter here, on the circle there, the angle there will be a right angle. There it is 90 degrees. I want to write it down. It is 90 degrees because of that sign. Angle in the semicircle here is 90 degrees. If this line here is a diameter, then that angle there becomes 90 degrees. But you need to be aware that if you have a circle like this, and you are told that that angle there is 90 degrees. Here you are given that this angle is 90 degrees. What does that mean? It means that this line must be what? A diameter. If the angle there is 90 degrees and it is given to us that that angle on the circumference, the semicircle, the angle there on the circumference of the circle, if it is 90 degrees, it is given to us that it is 90 degrees, then we know that this line must be what? A diameter. Or you are given that this angle is this line is a diameter, then we know that the angle there must be 90 degrees. Please be familiar with the diagram. It's very important for us to use it. It actually can also be used for the angle at the center subtended by the arc is twice the angle on the circle. This angle here is 180 degrees. Do you see that? Angle, straight angle is 180 degrees. The angle subtended by the arc on the center of the circle is twice the angle it subtends at any point on the circle. So this one is 180 degrees, that one must be 90 degrees because the one at the center is twice the one on the circumference of the circle. You also need to be aware of this theorem here. The theorem here says, talks of angles in the same segment of the circle. This angle will be equal to that angle. Please keep that in mind. They are subtended by the arc BC here. They will be equal. They are on the same segment of the circle. They must be equal. The same goes here. This angle here will also be equal to that angle here. They are also on the same segment of the circle. They are, you see the way I have indicated them, it is different. This is not equal to that, not at all. But these two are the same. They are equal in length because they are on the same segment of the circle. These two are also equal, subtended by arc AD there. Subtended by arc AD, they are also what? Equals to in size. If this one is 40 degrees, this is also 40 degrees because they are subtended by the same arc AD. Maybe related to those two theorems, I need to also indicate that be aware of this other theorem here. In fact, this other axiom here, corollary based on what we have learned there. It says angle subtended by equal chords. This chord is equal to that chord. These two angles will be equal. Angles subtended by equal chords. The chords are of the same length. You see they are indicated. Chord DE is equal to chord AB. These chords are equal. It means these two angles will also be equal in size. If angle C is 20 degrees, angle F will also be 20 degrees. Why? Because they are subtended by what? By equal chords. Please take note. It's very, very important to recognize that diagram as well. Maybe when you come to cyclic quadrilateral, remember that cyclic quadrilateral, it will always be indicated to us that A, B, C, D are the points on the circle. Once it is emphasized that those points are on the circumference of the circle, the points are on the circle, then we know that we have a cyclic quadrilateral. We have a cyclic quadrilateral. What do we know about a cyclic quadrilateral? The opposite angles of a cyclic quadrilateral, they will give you 180 degrees. They are the sum of two opposite angles of a cyclic quad. The sum of these must give you 180 degrees. The sum here must give you one. When you add angle B plus angle D, angle B plus angle D is equals to 180 degrees because they are opposite angles of a cyclic quadrilateral. They must give you 180 degrees. Please keep that in mind. The same still happens with angle A plus angle C. Angle A plus angle C, they are opposite in a cyclic quadrilateral. They must give us how much? 180 degrees. The sum, when you add them, they must give us 180 degrees. But we also know about a cyclic quadrilateral, this diagram here. It's important, the exterior angle, the angle outside a cyclic quadrilateral, the angle outside is equal to the interior opposite angle. The angle outside a quad is equal to the interior opposite angle. If we are given that A, B, C, D are points on the circle, they are on the circle, and CD is produced to E, produced. Let me write that, produced to E. If it is produced to E, then we know it's a straight line here. It is produced to E, a straight line. Therefore, the exterior angle will be equal to the interior opposite angle in a cyclic quadrilateral. Good. About tangents, we have also learned a number of theorems also about a tangent that we need to be very aware of. Always keep in mind, recognize the diagram. I'm just making rough sketches of diagrams. Recognize the diagram. Here that a tangent A will be perpendicular to the radius at the point of contact. Here where they meet, the tangent perpendicular to the radius at the point of contact. Here where they meet perpendicular, it means the angle formed there is 90 degrees. Please keep that in mind. The angle formed there is 90 degrees. Where the tangent meet with the radius. It may be the radius, it may be the diameter. Just be aware that at the point of contact there, the tangent and the radius will be perpendicular to each other, making the angle there to be how much? A 90 degree angle. Remember the sign here, it is for perpendicular, meaning 90 degrees. Good. One other theorem about the tangent that we have learned is the theorem like this one, that two tangents drawn to the same circle. You know, they are drawn to the same circle. You see the tangent there. They are drawn to the same circle from the same point outside the circle. Tangent drawn from the same point to the same circle. Those two tangents will be equal in length. The two tangents AB is equals to AC. And you will remember that when you prove this kind of a theorem, that's where we use what? That's where we use congruency. That's why I use congruency, because already we have here two triangles. And once we have two triangles, you know that then you can use congruency. We use congruency mainly when we have two triangles. That's what we said earlier on. Two triangles, congruency. So remember, look here, look here. Already there you have what? You have a radius and a tangent. They make 90 degrees at a point of contact. They are perpendicular to each other. Here, what do you have? You have a radius from the center to a point. They also make 90 degrees. So you have 90 degrees in that triangle. You have 90 degrees in this triangle. But this is a radii. That is a radius. Radius, radius. They are equal in length. Can you see that? And this side is common. This side is common. Therefore, the two triangles are what? Are congruent, meaning that this side must be equal to that other side in these two triangles. Let me color them so that you can see them very well. This is the first triangle here that we're talking about. You see that triangle? We are saying it can be proved congruent to this other triangle here. Those are the two triangles we have. But remember now, therefore, that ultimately the two tangents drawn from the same point outside the circle, they will be equal in length. Good. The other theorem about the tangent that we need to be aware of, tangent and a chord, A, B, C, we have T there, CT is a tangent, but the angle here, angle between tangent and a chord, the angle between tangent and a chord will be equal to the angle in the alternate segment of the circle. Angle between tangent and a chord will be equal to angle. If this angle here is 55 degrees, that angle A will also be 55 degrees. Angle between tangent and a chord, it is the tan chord theorem. Tan chord theorem, angle between tangent and a chord, here's a tangent and a chord. That angle between this angle will be equal to the angle in the alternate segment. Yes, I think those are some of the very important theorems that you must keep in mind together with what we have learned in grade 12 about proportionality as well as similarity.